Thank you very much. Let me also thank Suche and Samir for inviting me to this fantastic conference. What I want to talk about is some recent work I did together with Amir Iqbal, and hopefully towards the end also some two papers I wrote together with Ignatios Antoniadis, Yannis Foulakis, Kuma Narain, and Ahmad Senassi, which is about obtaining gauge theory partition functions from calculational techniques in string and M theory. So since this topic is a little bit orthogonal to what most other people are talking about in this conference, let me give you a little bit of what my personal motivation is for trying to get gauge theory quantities from a string theory approach. So my personal motivation is a class of superconformal field theories in 6 dimensions, the famous 2,0 CFTs, which since the discovery by Witten sparked quite a lot of interest. So they were introduced as the world volume theory of multiple coincident M5 branes. Just to give you a little bit of information what these theories are. So these are a class of interacting superconformal theories in 6 dimensions. The degrees of freedom are simply a set of tensor multiplets. Tensor multiplets have a number of scalar fields, fermions, and in particular a chiral 2 form in 6 dimensions. So it's a 2 form which has to satisfy chirality constraints. Since the theory is supposed to describe multiple M5 branes, so coincident ones which sit on top of each other, the theories are also generically non-abelian gauge theories. So there's a non-trivial gauge group which I will call G, and which is can be taken anything within the ADE classification. Moreover, as the name already suggests, the theory is a superconformal theory, so it transforms under the n equals 2,0 superconformal algebra, which has 16 supercharges. So that's a very well-defined setting for the theories.
So by gauge group, you mean that there is some group associated with the theory? Yeah?
Yes, absolutely, yeah. I mean, it comes just from the fact that you have a stacks of M5 branes rather than just separated ones. Physics-wise, there's quite some motivation to understand the theories better. First of all, things it describe, it's the world volume theory of multiple M5 branes. A better handling of the theory is likely to give us also a better understanding of M theory itself, and then by compactification, of course, also of string theory. So just from a conceptual point of view, this is a very interesting topic, and we would like to learn more about it. Also, the gauge theory community would be very interested in understanding the theory better, because it is believed that the theory is responsible for a number of interesting relations in lower dimensions, the first of which were the famous HET relations. So these are relations which connect quantities in various gauge field theories in lower dimensions. So suppose you calculate the partition function in a 4-dimensional theory and a conformal block decomposition in 2 dimensions, then it was found that these two are equal in several cases. The explanation for this is that both this 4-dimensional theory and this 2-dimensional theory are obtained by various compactification of the 6-dimensional 2,0 theory. So the 6-dimensional theory is sort of a parent theory which you can compactify in various ways, obtain different theories, and since they know both of them have a common origin, quantities computed in one match quantities computed in another. So in the recent years there have been many instances and many examples of such relations which have been found. And of course, if we could understand much better the 6-dimensional parent theory, that would give us a much better handle on these objects as well, on these relations as well. So that's quite some motivation for us to look into the theories and understand them better. The problem is, however, on a technical level, it is extremely difficult to describe the theories directly. And the main problem is that basically conventional, quote-unquote, quantum field theory methods fail due to the fact that we do not have a Lagrangian description of the theory. So till this point, till today, there is no known Lagrangian in 6 dimensions. It is speculated that, in fact, there is none at all. The reason behind this has essentially to do with the field content, so it's very deeply ingrained in the theory and lies with this chiral 2 form. Basically, what you can show is that it is impossible to obtain the chirality constraint for these two forms from the equations of motion in 6 dimensions.
So that would prohibit a covariant Lagrangian.
There is something which is called a Pseudo Lagrangian, which does not. This is a quantity which very much looks like a Lagrangian. However, the variation of this object with respect to the fields does not produce the equations of motion for you, but derivatives of the equations of motion. And then you can indeed formulate a chirality constraint. However, the quantity you started with is not a Lagrangian to begin with, so you can't stick it in path integral or something like that.
Because imagine just breaking covariance and writing a Lagrangian.
This has also been tried. So even I mean Lorentz covariance and so on. This has been tried. Of course, this opens a bunch of all other problems. One thing which I have been trying with collaborators is not to go in 6 dimensions, but to compactify the theory, go down to 5 dimensions. So there has been papers before that, and also with myself. And try to use a 5-dimensional approach to get information about the 6-dimensional theory. Of course, it is very hard in 5 dimensions to preserve all the symmetries of the 6-dimensional theories, and it's probably also not very. I mean, the class of quantities you can obtain from the 6D theory is probably limited. Even if you had a Lagrangian description in 6 dimensions. So if by some miracle you managed to find a way, it's probably also not very helpful in terms of traditional methods, because the 6-dimensional theories do not have a massless parameter. So your usual perturbative approach you have no parameter to organize a Feynman diagram expansion. So it's again very difficult and very hard to write down any meaningful quantities, to calculate quantities directly. So all of this points towards the fact that for this theory we have to think a little bit more outside of the box, and we have to come up with a little different method. And what I want to advocate in this talk is, let us try, since these theories are deeply connected with string theory, let us try to approach them from a more stringy angle. So is there a way to use calculational techniques from string theory to obtain quantities in that field theory? So let me make this a little bit more precise. If I say I want to calculate quantities in this gauge theory from string theory, what I mostly have in mind is, first of all, the partition function of the theory, but then maybe in later stages also more intricate quantities like indices, genera, supertraces, correlation functions. Of course, I would be interested from a string theory point of view, to do this perturbatively as well as non-perturbatively. So if there's a way to get a handle on non-perturbative effects from the string theory, this is possible, and this is also very welcome, of course. And I want to try to describe as much a larger class of theories as possible. So thinking about the 2,0 theory, you can think about deformations of the theory. A mass deformation is what I'm going to discuss later on. But then also you might try to describe other classes of theory falling into, along a similar spirit. Now, what kind of methods, what kind of tricks can I use from the string theory point of view? Well, there is a wealth of established methods that we have available. First of all, there are many interesting geometric approaches inspired by string theory. For example, calculation of elliptic genera, toric Calabi-Yaus, and the topological string defined on the toric Calabi-Yaus. There's a whole host of worldsheet methods like conformal field theory, worldsheet conformal field theories, the topological string, something which is called M-strings, which I will describe in this talk. And we have a whole host of target space methods, so mostly calculating of string amplitudes, the calculation of effective string couplings. All of these are very well established in string theory, so there are good techniques to work them out, to use them. And I try to convince you that this is very helpful and very fruitful for applications in gauge theory. And of course, there's also another corner which should not be forgotten, which is the extensive web of dualities and symmetries we have in string theory. So this does not only offer the possibility to calculate the same quantity, maybe in somewhat different guises, from using different methods in string theory, but it also might point towards new interesting properties in the gauge theory itself. So the dualities and the symmetries of string theory might in fact trickle down and tell us about some interesting new structures on the gauge theory side. So this points towards the fact that there is some wealth, there is some advantage to be gained by applying stringy methods to calculate gauge theory quantities. So what I want to do in this talk is I want to calculate mass-deformed gauge theory partition functions in n equals to 2 quantum field theories in 5 and 4 dimensions. So that will be the central quantity of my talk, the partition function of mass-deformed n equals to 2 gauge theories. And what I want to do is I want to describe a fourfold approach to these theories. So the first one is I try to argue to you that there is a way to obtain these theories from PQ brainwebs in type 2b string theory.
So by partition function, you mean the rest of partition function?
Yes, exactly. The full non-perturbative gauge theory partition function on the omega background, so using these Nekrasov regularization.
It's not the actual partition function. Gauge theory, right? So
Yeah.
it's an index.
Yeah, okay. The next corner I will reproduce the same results here from the topological string on some particularly elliptically fibered Calabi-Yau manifold, which is induced from this PQ brainweb. The third approach I want to advocate is something which is called the M-string picture, which was introduced by Waffa and collaborators a little while ago. So this is M5 and M2 in the intersecting M2 brains in some non-trivial geometry. And a fourth approach, which has also its merit, I think, is the use of scattering amplitudes within string theory to calculate gauge theory partition functions. This is a little bit, I've drawn this in a little bit of different fashion than the other ones, because while we have a kind of systematic way of studying all these PQ brainweb theories in all three approaches here, for the scattering amplitudes we are not that advanced yet, so we can only describe, we have examples of scattering amplitudes which reproduce some of these partition functions, but there's not yet a systematic way to cook up a scattering amplitude which precisely reproduces the partition function of a certain PQ brainweb. So for this talk, what I will do essentially is I will use this corner here as the definition of my gauge theories. So I will define them in terms of the PQ brainwebs. Their partition function can be calculated using Nekrasov instanton calculus, but I will not elaborate on this talk here because it does not quite fit the theme of modular forms. Rather, I will then use, after define the theories in these ways, I will explain how from the PQ brainweb it is possible to get elliptically fibered Calabi-Yau threefolds and then use the refined topological vertex to calculate the gauge theory partition function, which will have interesting modular properties. And then I will try to do the same thing using the M-strings pictures by calculating equivariant 2,0 elliptic genera. If time permitting, I will explain how these elliptic genera in fact also come from a certain class of string scattering amplitudes. A fancy name, I mean, these will be one-loop heterotic amplitudes. One loop type 2 amplitudes. A fancy name for this one loop amplitude, you could think of the partition functions arising from some singular theta correspondence from the equivariant elliptic genus. And if time permits, I might also discuss about another amplitude where I just reproduce the Nekrasov partition function without the mass deformation. So here I have two examples. Time permitting, I will probably only discuss one of them. So these quantities have also interesting symmetries. So there is an SL2Z symmetry which comes from the type 2 side here, which trickles down in a fiber-based duality on the topological string side, and is also ingrained in particular symmetries of the geometry of the M-strings picture, which will lead eventually to interesting dualities, which I will also discuss in all three settings. But now let me start with, as I said, with a definition of my gauge theories, and let me start with the PQ brainwaves. So, as been discussed in the literature, you can realize five-dimensional gauge theories on PQ5 brainwaves in type 2. So here I've schematically drawn the coordinates x0 through x9 on R1,9. And I take a number of D brains, which are stretched along x1 to x4, and in the x5 and the x6 direction, and a number of NS5 brains, which also stretch along the x0 to x4 direction, also stretching in the PQ brain, into PQ plane. So here's the plane which defines the charges with respect to the PQ web. I have a transverse R3, and in those five directions where which are common to both brains, this is where eventually the gauge theory will emerge. So let me zoom in a little bit here and explain the details of this. So to be specific, I will take M parallel NS5 brains and N parallel D5 brains. I will take these x5 and x6 directions to be compact, so I will compactify them on a torus T2. So all these directions here and these directions here are periodic. Then I can, of course, spread out these brains along these directions, and this gives me parameters AI running from 1 to n, which label the positions of the D5s along the circle along the x5 direction. I can do the same thing with the NS5 brains, so there are parameters labeling the position of the NS5 brains on the transverse cycle along x6. And these can, of course, be translated into the quantities entering the gauge theory. So particularly if I take all the distinctions, all the positions to be distinct, I will have a gauge theory with gauge group U1 to the n, and the AI and BI will be rated to the coupling constant and the Coulomb branch parameters of the theory. So these parameters, the geometrical parameters I read off from the web here, they will directly enter into the definition of my gauge theory. A generic PQ brainweb in principle has n equals 1,1 supersymmetry, so they will have only 8 supercharges. However, since I've compactified things on a circle, there is in fact an enhancement to n equals 2,2, which is double the number of supercharges, which is due to a massless sector, massless bifundamental hypermultiplets in the D5 sector. I will not treat this, so I will break this supersymmetry back down to 8 supercharges by introducing a mass parameter m. So how do I do this? In fact, I take a similar setting as before. So the red line are again just one of the NS5 brains, and the green lines are still my D5 brains. However, what I did now is I split each stack of D5 brains. So I introduced this little blue curve in here, the length of which corresponds essentially to the mass of these hypermultiplets in the D5 sector, and which is equivalent to the mass parameter. So I deformed my web a little bit by introducing these tiny blue curves in here. And there's one further simplification which I take. I take this blue line to be identical in all cases. So in principle, I could take a mass parameter m1 here and another parameter here and yet another one here. However, for simplicity, I will assume that all of them here are identical. So I just introduce one parameter m once and for all. This is a simplification. In principle, it's not necessary. You could also do more generic things. Having done this, what's the spectrum of my theory I get? The spectrum of the theory is, first of all, the gauge group is given by essentially m factors of SUN gauge groups. And since everything is compactified on one circle, I still have one U1 rotational symmetry left, which is an U1 factor outside. And the matter fields that I'm left with are essentially hypermultiplets transforming in this representation here. So it's a direct sum from A running from 1 to M with the n-dimensional fundamental representation of the aether, the anti-fundamental representation of the A plus first SUN factor here. Now, this seems a bit of singling out, say, the number of D5s or the number of NS5s here. In fact, due to the SL2Z symmetry of type 2b, there's of course also a dual description of this, which basically just exchanges the number of NS5 branes and D5 branes. So instead of M NS5 branes I had on the previous transparency, I can also look at the same setting with N NS5 branes and ND5 branes going to MD5 branes. What I end up with looks very similar, except for M and N being interchanged consistently. So I have a gauge group which is U1 times N factors of SUM. And the matter transforms now in, is made up from hypermultiplet transforming in the in this representation, where now M is the M-dimensional fundamental representation of the aether A plus first gauge group, SUM gauge group here. In terms of the parameters that I introduced before, so in terms of the distances of the branes along the dual cycles, there's of course an interchange. So what was the Coulomb parameters before, which were the differences of the D5 branes, now becomes the gauge couplings, and what was the gauge couplings before now become the Coulomb branch parameters. So there's a very obvious and very direct duality map between these two theories. The theories you can study along the lines of Nekrasov. So there is a very clear-cut way of how to obtain the instanton partition function for these gauge theories. This essentially uses localization techniques. So you compactify the theory on the omega background, which localizes your instanton, the integral over the instanton moduli space to certain saddle points, and these you can sum up explicitly. This was done by Nekrasov. I don't want to review it here. Instead, I want to go back to my web here and want to now describe the theories, which are defined just in this corner, now from another perspective. And the first thing I want to do is reproduce the gauge theory from the topological string on an elliptically fibered Calabi-Yau, which is related to this PQ brane web. So the claim is, to each PQ brane web that I just discussed on the slide before, I can immediately assign a toric non-compact Calabi-Yau threefold. So let me explain this with the simplest example, which is just the conifold essentially, which is m equals to n equals to 1. So the procedure is just draw the PQ brane web now with the deformation here, and draw the dual diagram to it. So draw edges orthogonal to all edges of the web diagram, and replace vertices with faces and vice versa. So this lands me on something which is called the Mutant Polygon. So it is the vertices are these faces here, here, and here, and the lines orthogonal to the lines of the brane web is just this square here. And in fact, I not only get the Mutant Polygon itself, so this line here, but I also get a triangulation coming from this mass deformation here. So I end up with a triangulated version of the Mutant Polygon. The next step is associate to each of the vertices of that Mutant Polygon vectors in an integer lattice Z3 in a Z3 lattice. So here I just take these two-dimensional vectors v1, v2, v3, v4, and just add a z1, a z equals a third component, which is equals to 1. The fact that the Mutant polygon is closed, that it's a two-dimensional polygon, will trickle down later on to the fact that what I'm constructing here is a Calabi-Yau manifold. So the fact that all of these vectors, if you wish, lie in one given plane, that will trickle down to be the Calabi-Yau condition for my construction. Moreover, these vectors essentially construct a cone C, a solid cone, which is just defined as in this way. And the triangulation here constructs additional cones for me. So over each of the triangles in my triangulation, I can define an additional cone sigma I. So here I have V1, V2, V3. Over that triangle, I can define one cone, say sigma 1. And similar over the triangle V1, V2, V4, I can define another cone, sigma 2. Given these subcones, I can associate to them patches in C3 just by dualizing them. So just by defining the dual cones in this manner, I get immediately patches in C3. And the toric Calabi-Yau which I get is simply obtained from these C3 patches by gluing them together, following the rules of how the sigmas in my original Mutant polygon were glued together. So that the fact that the sigma 1 here and sigma 2 were connected along this triangle coming from this triangulation gives me a rule of how to patch together the dual cone sigma I. And if you work this out all for in this case, you get essentially these two patches with one condition labeling governing the dependence of the complex parameters x1 to x4, and that's essentially just the conifold equation. You may ask the question, what happened if I had started from a dual PQ brainweb? So what happened if I had started from a PQ brainweb like this? Well, things would have worked essentially the same way, except for the fact that I would have a different triangulation of my Newton polygon, which trickles down to a slightly different patching of the Calabi-Yau at the end. So that just ends me up being ending up in a dual Calabi-Yau setting. That was the simplest case, of course. So of course, if you take a more complicated PQ brainweb, you will get much more complicated Newton polygons, but the procedure is essentially identical. Generically, however, what happens is that you will still end up with a singular Calabi-Yau manifold, so you will still have to remove the singularities, and for our purposes, I will still have to compactify it on a torus. So let me briefly go through these slightly technical steps. So for the conifold, you have, of course, two possibilities. Either you deform or resolve. In a deformed setting, what you do is you take the equation I had on the previous transparency and just deform it by a parameter epsilon. This allows me to split this equation in two ways. So in a more suggestive way, I can write it like that. So I can write the product of x1, x2 equals z, and x3, x4 equals z minus epsilon for complex variable z. And geometrically, each of these equations basically defines for me a C star cross C star fibration over the z plane, which degenerates at 2 points, and exactly epsilon equals to 0, and z equals to 0 and z equals to epsilon. So on a generic point, I have these C2 cross C star cross C star fibers, and which degenerate at these 2 points. The line connecting them is essentially an S3. How you can see this is by just writing the defining equation up here in a slightly different way. So writing them in complex coordinates, Z1 to Z4, and doing a coordinate transformation in this way, so splitting Z into real and imaginary part, you essentially get these two equations, and the section ui equals to 0 trivially satisfies this equation and just turns this into the defining equation of S3. So that's just the 0 section, and the full deformed, from this you can read off that the fully deformed conifold is then just the space of the cotangent bundle on S3. So that's the geometric definition. That's the deformation of my Calabi-Yau. Finally, for the applications I have in mind, I still want to compactify this on a torus. So instead of a C star cross C star fiber, I now compactify them on a torus with the same idea. So along on the Z plane, I have 2 points, Z equals to 0 and Z equals to epsilon, on which either of these two tori degenerates. So what I described for you in quite some detail now is the simplest case, the conifold, which the resulting Calabi-Yau will denote x11. The more general case I will denote by xm, n. So if I started from an m, n PQ brane web, I will end up with a toric Calabi-Yau manifold xmn. And it was shown in this paper that in fact they can be related back to the x1, 1 case through a Zm cross Zn orbifold. And of course, as I pointed out, you can also describe the dual Calabi-Yau just by starting from the dual PQ brane web in the beginning. Okay, now that I have my Calabi-Yau manifold, let me obtain the partition function by using the topological vertex mechanism. So for a generic, so the refined topological string was topological string vertex was introduced by Hollowwood, Iqbal, and Bafa, and the idea is to build up the contribution for a generic brane web, for a generic MN brane web, by looking at smaller building blocks. So let me look at one of these webs. Let me remind you of my notation here. So the blue guys are the mass deformation I introduced some time earlier. I will use the notation that Qm is e to the 2 pi im. And the parameter distances of the D5 branes I had here, they were the parameters AI, AJ, and I will package them in Qj in this form. And to save myself some writing, I will collectively denote them just by boldface Q. Now, given such a brane, such a web, the idea is to calculate the building blocks for one of these slices here. So I just chop off one row like this and define myself a vertex building block of this form. So this vertex building block, of course, will depend on, of course, the mass parameter, the deformation parameters, the distances here, and two parameters, epsilon1 and epsilon2. They are due to the refinement of the topological vertex. So from a gauge theoretic point of view, they implement the omega background. So from a field theoretic interpretation, this is sort of a regularization procedure, a geometric regularization procedure where you define the gauge theory on the omega background, so the corresponding parameters you see here. Moreover, the external lines here, they will be labeled by alpha 1, alpha 2, up to alpha n, and beta 1 to beta n. In the vertex formalism, these correspond to external states of the vertex. So each of these 3-point vertex here will then replace by a topological vertex. And each of these external states will be labeled by essentially integer partition functions. The idea here is that you can describe the vertex from a two-dimensional sigma model, and each state in this sigma model is essentially identified with an integer partition. And all of them are labeled by alpha 1 to alpha n. So given this W, you can just glue them together. So the whole partition function, topological string partition function of this PQ brane web is essentially just obtained by gluing together the building blocks I defined here, weighting them with the moduli of the parameters here. So the notation here is a bit intricate. The sum over alpha here is the sum over all these external lines for one of the building blocks here. The W's themselves, I also have written in a somewhat condensed notation like that. So instead of spelling out all of these indices, I've just written alpha to the A. And the norm up here for each partition, that is essentially, so if I have a partition alpha of length alpha, then the sum over all elements of this partition, that's just the norm of alpha which appears here. More explicitly written, so the W's here, there's an explicit formula which you can just, by gluing together one vertex after the other and summing along the blue line, you can write it in this form. So you see here, you have the product over various vertices summed over mu and nu, so over these mu and nus here. And each of the individual vertices is built in this way. So they're essentially just combinations of the skew-sure function. I apologize slightly for the notation here. Little q is not e to the 2 pi I tau in this case, but it's following the conventions of the topological string vertex people. It's e to the 2 pi I epsilon 1, and t is e to the minus 2 pi I epsilon 2. Apologies for these somewhat strange conventions, probably. Right, so, and set tilde, which appears here, that's essentially a slight generalization of the McMahon function. It's just this product, which is just depending on epsilon 1 and epsilon 2. So the point is, sorry for being a bit technical here, but the point in all of this is this works for a very generic brane web. So I never had to specify exactly what is M and N here. So how many building blocks I have in this row or how many building blocks I have in this column. It's just a combination and a patching together of the simplest topological vertices, which is just the 3-point junction here.
So with the mass definition only appears outside the sum.
Yes, it just appears, well, it appears in each of these junctions here. So it appears in one of these chopped things as a sum, a sum along the blue line. So you patch together two of these C's, and each of these leg C is weighted by a mass-deformed parameter Qm. If you then patch along the green lines together, there you only get the moduli QB, so the really geometrical moduli. But the mass parameter indeed only it appeared along the blue line, which is exactly appearing if you patch together these two C's. You weight them by a QM factor. Any further questions? Right, so that's a very that's a very algorithmic way. You can just take this and, build up by building blocks whatever geometry and whatever brainweb you want to have in a very straightforward manner. Explicitly, what you can also do is you can, after doing the sums over the partitions, you can massage them in a slight way and write them, in fact, as quotients of theta functions. So you can show that the generic form for an MN brainweb has, there is first of all a weighting factor going to the power of m, which is just the contribution, the perturbative contribution, the U1 perturbative contribution, if you wish, which is just the contribution which has only empty partitions as external legs. To the power m, so that's a universal factor, if you wish. And then it's this contribution here, summing still over numbers of partition, weighted by the Kähler parameters, and then it's these quotients of theta functions. This quantity written in this way, if you forget about the guy here, they have interesting modular properties. So first of all, there's a non-holomorphic, if you use a non-holomorphic completion. So if you complete each of the theta functions you see here non-holomorphically, so if you write, for example, theta 1 as the exponential over these Bernoulli numbers with Eisenstein series E2, and you replace E2 by E2 hat in this way, this quantity, without the M, this guy here, this quantity becomes modular, and in fact it becomes...
So that you only display one argument of the theta function, so the tau argument is what is Q?
You see, I have multiple QAs here, so U is just a placeholder here. Take each of these theta functions here, and I just...
What is that then? There are two arguments. There is QT out here. That's the quote unquote. That's what would be tau in here. Sorry for this confusion. There is the T I have here. That would be the Z argument in here, which I dropped, and the U is just the collective parameter of one of these here. Sorry for that confusion. Right. If I do this completion like that, so if I do this non-holomorphic completion of that form,
then that quantity here becomes invariant under a modular transformation of that type. However, there's quote-unquote a holomorphic anomaly. So there is, if I hit the z hat, so if this guy with the E2 hat derivative, then what I get is a second order differential operator in the moduli, a QBI acting on z hat.
Sorry, I don't understand fully.
Okay, sorry.
Yeah, can you explain what is U in terms of the original equation?
No, U is one of these scalar parameters I have here. I mean, I have.
The last equation is one equation. It's not for the whole thing. So
Yeah, take U, one of these parameters I have here. Then since I have non-holomorphic completions of this type for each of these parameters, I see a E2 hat dependence on each of them. And they are defined by a second order differential operator of this type.
but
I mean-
what's the physical meaning of this modularity? On what parameter does it act?
It does act on the scalar parameters in the on the AI, which are just the differences. It acts on the T, which the U here, and it acts on the mass parameter in this way. So that's the transformation I'm doing.
Yes, everything is clear, but
It's U that is not clear. What is the meaning of it?
I mean, the simplest case. Sorry. You can. Okay, let me tell it like that. You can relate to the radii of the torus I had. I mean, take the simplest case. Take just U to be on the torus. Remember, I compactified my Calabi-Yau on the torus. Then take just U to be the complex structure modulus on this torus. That's the simplest case. Does that?
So I have another question. So these theta functions are just regular theta functions.
Yeah.
And it's that prefactor which is causing the.
That's right.
Because the portion of the theta functions without doing any replacement is.
That's right. That's right. That's right. Yeah.
You said the effect of the prefactor can be observed by doing this.
That's right. That's right. Other questions? Okay. I will write an example in which hopefully makes some things more clear. I mean, the m equals 1, n equals 1 case a little bit later on. But before that, let me press on and go to the M-strings picture. So this is an idea which was brought forward by Waffa and collaborators some while ago. So let me look at the setting where I have multiple M5 branes and M2 branes in 11-dimensional M theory. So I have geometrically coordinates y0 to y10. I have a transverse R4 here. I have the 6th dimension compactified on S1, and I have a parallel F4 here. And the space where the M2 branes and the M5 branes overlap, that's what I will call the M-strings world sheet.
So Stefan, can we just go back to the.
Yes.
So with this substitution, you're actually spoiling the modular properties of theta 1. Right? So as to sort of compensate for the bad modular transformations of the prefactor. I mean, theta 1 without any. I'm just, or is this an equation? I'm just confused.
No. I mean, the statement is. I mean, some of these theta functions here, you can write them as exponentials of B2. I mean, in this form with the Eisenstein series. So that as an equivalent form of writing this in terms of Eisenstein series. Some of them will have also depend on E2. So that spoils modularity because E2 itself is not.
So then they're not the regular theta.
These ones are not. They are built from regular theta functions. Sorry, I probably said this wrong before.
No, it's not
Sorry.
the same data here.
Yeah, sorry. Then I misunderstood your question before.
So the thetas in your main formula are not the usual theta functions.
No, they are built out. They are built out from the regular ones. But in order to make them modular, you have to do this substitution.
They're built in a non-modular way.
Yeah. Sorry. Then I misunderstood what you asked before. But if you do this substitution, you get invariance under these transformations, but you buy this non-holomorphicity.
And the theta 1 here is also not the usual theta 1.
Not written in this way, no.
Is this the odd Jacobi theta function?
No, this.
E2, right? So it's,
Yeah.
it can't be.
So it's not, right?
Yeah, it's
so
not.
Yeah,
some,
yeah.
some
E2 is not. Why do you call it theta 1 and not
Yeah, that's
If you have E2,
if it,
Yeah,
you have
yeah,
that
yeah.
distribution.
Exactly, yeah.
If you take the usual theta 1, you do get E2. That's some exactly.
Okay, right. So back to the M strings picture. So graphically, what this means, I have take stacks of several M5 branes and separate them along the Y6 directions, which is the circle here. So I have multiple M5 branes here, and I have stacks of M2 branes in between them. Then what Waffa and company, so what these gentlemen called the M strings, is if you look at the M2 branes ending on the M5 branes, then what they sweep out here is just the one-dimensional manifold, which is called the M strings. So what they argued is, let us describe this whole system from the perspective of the world sheet theory of these strings, which is termed the M strings picture. The motivation here comes again from the 2,0 theory, where in one way you can describe that theory using dimensionless strings from the M5 world volume theory. So you want to describe the theory using the essential degrees of freedom, the tensionless, a bunch of tensionless strings. And one way of getting them is using these M strings here. That's the motivation in this paper. In a follow-up paper, what they argue, if you want to separate the M2 branes also in the transverse space, this can also be done. However, you have to use some kind of orbifold techniques for that. Yeah, so that's what they were arguing. If you want to have distinct stacks of M2 branes, then you can do this through orbifolding the original theory. This was a follow-up paper written by them. The punchline, however, what they argued in the first paper is if you have this, so if you look at this paper, then you can calculate the gate theory partition function through a two-dimensional sigma model. And the equation you find for generic M, M is like this. So the setting is you have M parallel M5 branes and N distinct stacks of K2 branes, each of which has Ki branes in the I stack. So this explains this number as K here. Then the moduli dependence enters as this prefactor phi k here, where I used again in the condensed notation. So phi I are the moduli of my setting. Chi elliptic here is something which is called the equivariant 2,0 elliptic genus with the target space M and K, which is the product of the SUN instanton moduli spaces, each of which has charge K. And another crucial ingredient is this vector bundle Vk here, which is also crucially determined the geometry. So there are two important inputs here. So it's the elliptic genus of the product of these SUN moduli spaces, but each of them again weighted in a certain way by a vector bundle V. So let me explain this a little bit more in detail. So if I want to discuss the 2,0 elliptic genus, but let me start explaining to you a 2,2 sigma model. So if I had also supersymmetry on the right moving side. Then I can write it as a sigma model with Kähler target space and Kähler potential like that, where the degrees of freedom, so the chiral superfields are just maps from the world sheet into the manifold M, in such a way that the bosonic guys, the phi i's, are just the coordinates on M, whereas the psi i's they are spinors on the world sheet here, on the two-dimensional manifold, whereas they are vectors on M, and they are just basically sections of the canonical bundle on M times the tangent bundle on the manifold M. So these are the psi i's, and similar for the psi bars. It's just the conjugate to that. What happens in the 2,0 theory is that the right-hand side of these moduli is slightly modified, and instead of the tangent bundle of the manifold, you now have this particular bundle V here. So the fermions of your 2,0 theory are defined sections of this canonical bundle times the, this holomorphic line bundle on the right-hand side, V. So it's important to determine that, which I will do in a second. The elliptic genus itself can be written as a trace in that, in the usual way as a trace over this sigma model, where now introduced Q as e to 2 pi I tau and y e to 2 pi I z. And it can be evaluated geometrically as just an integral over the manifold of these, with these theta functions, where the xi's are just the Chern roots of, which you obtain by expanding the Chern character either of the tangent manifold or of this bundle V. So the bundle V here enters crucially through these X tildes. Let me make a few more words about what I mean by equivariant elliptic genus then. So as we know, the elliptic genus of a compact manifold M with a vanishing first Chern class, that's a weak Jacobi form. So it transforms in the well-known way under SL2Z transformations, as we've seen many times already in this conference. However, if I have a non-vanishing first Chern class, then that property is lost. So that quantity is no longer modular. However, by Gritsenko, it was an automorphic correction was introduced, which he termed the modified Witten genus. So it's defined in this way. So theta 1 here is the real theta 1 function. You have this prefactor. And then you have an integral over M of these two factors M and N, where X are just the Chern roots I had introduced on the previous slide. And P is just this exponential of derivatives of the Weierstrass function, and W is this function of exponential of the weighted Eisenstein series in this form.
Compact manifolds or?
This is for compact manifolds. The problem, of course, appears in the integration if you have a non-compact manifold. However, if you have a non-compact manifold which happens to have a U1 action, you can evaluate that integral equivariantly. So just as a sum over the fixed points of this U1 action, where each fixed point is weighted by a certain U1 weight, which is exactly what is determined from the bundle I had some while ago. So the weights of this equivalent action, that you can read off from the bundle I had defined in the previous slide. So what is that bundle? In the original paper by Waffa and company, they did just the case n equals to 1. So if you have just one stack of M2 branes coming in and another one coming out, they argued that the correct bundle is given by this product of the X group and the canonical line bundle in this way. So they proved if you use that bundle and stick it into the equivariant elliptic genus, that gives you the correct partition function. I don't have a very good intuition about arguing for these X groups. One explanation which came from earlier from Katz and Sharp is the X group essentially, they count the massless open string states between various D-branes. So if you have D-branes, if you have a manifold X and submanifolds S and T with fibers E and F over it, then the massless states of open string states between these branes, they are counted by these X groups. So these X groups know about a number of massless states, and thus it seems very likely that they indeed enter if you want to calculate the partition function. Fact is, however, if you take this bundle and use it just for calculation, it works out very well. What we did is you can generalize this picture. So if you have several stacks of branes, you can just form this bundle here. So you just take sums over various X groups. And for each of them, you can work out what these weights are that I have presented in the previous slide. And the claim is for all the cases that we checked, and we checked quite a number of them, this bundle is exactly the correct one, which reproduces for you the partition function.
It's just the bundle that comes in the ADHN construction. It's not white space?
Yeah.
With flavor?
I think without flavor to begin with, but yeah, I think at least here that's true. Here we did not check. Right. So now I have produced three ways, at least two ways, for you to calculate the partition function. Let me now look at the simplest example, and let me look at m equals to n equals to 1. So you can calculate the log of the partition function with either of the methods we had before, and it gives just this double sum here, where I now introduce the scalar parameters of my torus with e to minus t. I have the mass parameter, and I have the epsilon 1 and epsilon 2 being now parameterized in a slightly different way in this form. You can make a genus expansion of this. So since I had T1 and T2, both of which depending on the GS, you can write your F in this way with each of the free energies Fg given in this form with the explicit coefficients like that. So there's each of the Fg's, which appears here depending on beta, has this factor made out from the Bernoulli numbers, times some additional factor which vanishes if you take beta equals to 1, which I'm going to do in the following. And the same thing for these factors HE here. You get a factor of that type times plus again something which vanishes for beta equals to 1. Let me massage this equation a little bit so you can prove that you can write it in the form of these polylogarithms. Each of, in this Lie 3, 2 minus g, so generalized polylogarithms, and each of these guys comes weighted with the Fourier coefficient dg for beta equals to 1, which are built out from the factors I showed before. So here again you get these CG factors depending on the Bernoulli numbers, and here as well. And if you work out, for this case, the equivariant elliptic genus for C2 with a U1 action along the origin, you exactly reproduce this expression here with the real θ1 function. And if you do a Fourier expansion of that, you indeed exactly get the same dg's. So indeed, this Fg comes exactly from this equivariant elliptic genus.
What again is the interpretation of this modular parameter tau from the point of view of the cross-self function, just the previous slide?
Here it's q rho. I mean the tau from the equivariant parameters just goes into the q rho.
Q rho is what is the gauge calculator?
Is the scalar parameter. I mean, I have the torus compacted.
Just in the language of the gauge theory, and the cross-self, what is this parameter?
That's the gauge coupling indeed. In the setting you have here, I mean, you have two sets of parameters. You have the gauge coupling and you have one Coulomb punch parameter, and the q rho in this case is just the gauge coupling here. Okay. How I'm doing with time actually?
Well, you have 15 minutes or so, a little more.
15 minutes, okay. So this integral here, one way, so we have this equivariant elliptic genus and we have this form of the free energy. So what you can show is you can extract the free energy from the equivariant elliptic genus in another way using a Torus integration. So if I define this integral here, so I just take the elliptic genus of which I presented on the previous slide. I multiply it together with a 2,2 Narayan lattice where Q is e to 2 pi I tau here. P left is, I didn't write them down, P left and P right are left and right moving Narayan lattices. And I weight also the arguments of the elliptic genus with these P rights. This is invariant on a modular transformations of, so this is a well-defined integral if I integrate it over the fundamental domain of SL2Z. So that's just, that's a well-defined quantity. And the T and U I see here, these are the moduli of my Narayan lattice. So these are the T and U entering in P left and P right. And if you evaluate this, so there are well-defined very well-studied ways of performing this integration. And if you do this integration, taking the limit u to infinity, you exactly recover the free energy as before. So upon, of course, identifying the moduli explicitly. So what happens is it's possible to get the gauge theory, the free energy, the logarithm of the gauge theory partition function, also from a torus integral of that type. And these torus integrals notoriously pop up in one-loop amplitudes in string theory. So that's the reason for our fourth approach, namely, is it possible to come up with scattering amplitudes in string theory, which exactly produce integrals of the type I just shown, which produce at the end the partition function of my gauge theory. So that's the inspiration for the fourth approach. As you can tell from what I said, this is not an algorithmic approach, so I cannot do it for any PQ brain web. I do not immediately know what the corresponding scattering amplitude is. But in simple cases, and the n equals to 1 case is one of them, it is easy to cook up an amplitude, to arrange amplitudes in such a way that they exactly produce one loop worldsheet integrals of that type, which ultimately give me back this partition function. So I want to show two examples, probably only one example here, which is the free energy for a single M5 brane, just what I showed to you. This is directly what I just discussed above. I will show to you that there's indeed a one-loop amplitude in type 2 string theory, which reproduces as an integrand the equivariant elliptic genus, such that its worldsheet integral gives me the partition function. In more mathematical terms, this goes by the name as a singular theta transform. So the gauge theory partition function arises as a singular theta transform, as a theta lift, if you wish, from the equivariant elliptic genus. And this might have interesting relations to moonshine or the algebra of BPS states. I guess I will skip the second example, so let me just go with the first example here. So the amplitude we found together with Iqbal, based on earlier work with Stefan Stieberg, is of this way. So that's now really a one-loop scattering amplitude in string theory. It's a very convoluted amplitude. It has many insertions. So we have insertions of two gravitons in the form of two Riemann tensors. We have a set of n Kaluza-Klein gauge fields which come from the compactification of the torus. So this is type 2 string theory on T2. So I have kk gauge fields on the torus. I also have a bunch of massive string oscillator excitations. So these are excitations on the left moving side, so on one of the sides. And I have massive deformations of the torus scalar. And to make all the ghost pictures work, I also have picture changing operators just to balance out all the ghost charges. So this is a one loop amplitude. It is a two parameter family, in fact. So it has the parameters n and m here, and k. So I have these parameters to play around with. And what you can do is you can explicitly work out these calculations, which I'm not going to attempt to do for you. And what you can show is that this amplitude, after you've done all the calculations correctly, is just a certain u bar derivative of the integral I discussed for you before. So this imnk is exactly the integral I had appearing a few transparencies ago. So indeed, I have a string scattering amplitude which exactly relates to the torus integral, torus integral which reproduced the gauge theory partition function. So I indeed get a very direct relation between string loop amplitudes and QFT partition functions. The problem is, as I said, there is no algorithmic way of guessing these forms. So this is just essentially cooked up. This is an amplitude designed in such a way that this relation at the end of the day holds true. And at the moment, we can only do this using trial and error. But we hope to improve this, of course, and get a better feeling of what factors you have to put in order to reproduce generic PQ brainwaves. I will not discuss this because of lack of time. So let me...
You have quite some time.
I still have.
Yeah, I mean, you have 15 minutes.
Still,
10
okay.
minutes.
Along the spirit of that, I want to show you a slightly other example, which is not exactly along the lines of examples I discussed before, but just to show you that this idea of partition functions works indeed out, which is getting the Nekrasov partition function from string theory. So the four-dimensional gauge theory partition function without mass deformation. So let me switch that off. You can calculate it, as I already said, using localization techniques on the so-called omega background. And that's a theory which propagates in 4 dimensions vector multiplet with an SUN gauge group. The omega background is a particular compactification on a torus characterized by 2 parameters, epsilon plus, epsilon minus, as I had them before. And this U1, the omega background is special in the sense that it also preserves supersymmetry. So this deformation is written in a very cunning way to preserve supersymmetry. This gauge theory partition function already has a very interesting connection to string theory. Namely, there is a class of higher derivative scattering amplitudes in n equals to 2 string theory on some Calabi-Yau elliptically fibered Calabi-Yau in type 2, which is just propagating 2 self-dual Riemann tensors and 2G minus 2 anti-self-dual graviphoton field strength tensors. These capture the free energy of the topological string. So that's an old paper by Antoniadis, Gavanara, and Taylor, that exactly the FGs you have here, they are exactly the genus G free energy of the topological string on your Calabi-Yau compactification X. If you take the gauge theory limit of these FG phi's, so if you do a genus expansion as before, and take the gauge theory limits, field theory limits, a point particle limit from a string theoretic point of view, you exactly reproduce the partition function, the Nekrasov partition function on this 4D gauge theory on this omega background. However, not with the generic parameters epsilon plus and epsilon minus, but with one of them being set to 0 and the other one being identified with the string theory, with the topological string coupling. So these FGs have already a well-known connection to partition functions along the lines I also discussed before. The question which of course remains, what happens to the other parameter epsilon plus? I mean, here it's set to 0. Is there another class of amplitude which allows me to get the full Nekrasov partition function? And does this also maybe tell me something about the generalization of the topological string? Something which goes by the name of refined topological string now. The answer is yes. So what you have to do is you refine these couplings. So on top of the Riemann tensors and the graviphoton field strength tensors, you now also add vector partners of the T modulus. So think of this as now an amplitude in heterotic and K3 times T2. Then Ft is the vector partner of the T modulus of the heterotic T modulus. The claim is if you calculate these amplitudes, which is starts appearing at one loop in heterotic string theory, calculating it, which is quite a tricky calculation, and taking the field theory limit, you indeed explicitly reproduce the full Nekrasov partition function. So here you have another example of a string theory amplitude which tells you something about a gauge theory partition function. In this case, we got a little bit ambitious. So in fact, if you look closely, I wrote here the perturbative part of the Nekrasov partition function. And with my collaborators, we got a bit ambitious and asked the question, okay, what about non-perturbative contributions to this to this coupling on the string side? So that, as I said, this is a one-loop calculation we did here to obtain this result. And if we can extract some non-perturbative contributions here, do they tell us anything about the full necros of partition functions? So not only the perturbative part, but also the non-perturbative one. And in brief, the answer is yes, this works out. So if you go to a dual setup of type 1 on K3 times T2, say, and you realize the gauge theory as D9 branes with D5 instantons on it. So you have a setting in which you have n space-time filling D9 branes and D5 branes wrapping essentially all of the internal manifold. Then you can calculate gauge theory instanton corrections to the coupling before simply by looking at string tree-level diagrams. So these are disk diagrams which have some of the say D5 vector moduli as their external states. Oh, excuse me. And as an insertion, they have either the graviphoton, which was one of the deformation parameters, or the T-bar vector, which we had before. So if you only take the graviphotons here, then you reproduce indeed gauge theory partition functions with only one parameter, say epsilon minus. If you also include the T-bar vectors here, you indeed, if you calculate all of these disk diagrams and sum them up correctly, what you reproduce is the full epsilon-deformed ADHM action in the field theory limit. So take the combination of all of these disk diagrams and take the gauge theory limit, and what you reproduce is the full ADHM action with both parameters epsilon plus and epsilon minus switched on. And from that ADHM action, you can do exactly what Nekrasov did, so use localization techniques and reproduce the full Nekrasov partition function. So this is not only the perturbative part, but also the non-perturbative part. So this is an example of a string amplitude, string couplings, which in a certain limit reproduce for you also non-perturbative effects from gauge theory. Okay, let me conclude here. So what I did in this talk is I discussed for you a fourfold approach to gauge theories from string theory. I showed for you several equivalent ways of computing partition functions. I tried to make effective use of string symmetries and dualities and using various approaches from string theory reproducing the same answer. I described a relatively large class of theories for you, and I tried to convince you that this is also possible beyond just perturbative results, both from the gauge theory as well as from the string theory. For the future, it would be, of course, interesting if it's possible to access other quantities, not just partition functions, but other some correlation functions, indices, genera, whatever, that you can calculate with similar techniques. Is there an extension of the examples we've known? So here I've described these PQ brainwebs. Are there other classes of theories which we can describe equivalently, I mean, with similar generality? And then there's the question, is there any connection which I can make to mathematical aspects of string theory, like moonshine or BPS algebras and so on? Thank you. You mean, do I have any additional insights into the world sheet theory? This, I'm afraid, is not. I don't have. I mean, so far we did not take away any more information about the multiple M5 brane theory as such. But what you can do with various string methods, without having direct field theory access to it, you have many methods which can calculate for you quantities of that gauge theory. As I said, here I've presented for you calculations of mass-deformed partition functions of that theory. That's one quantity you can calculate. The hope is you can do more of these. So, I mean, calculate other quantities, calculate correlation functions, and so on. The punchline here is, for all of this, I do not need a theory, a Lagrangian description for that theory. I just used rather well-established string theory methods to compute something into which I would not have access using some traditional methods. So the punchline, if you wish, what you might want to take away here is don't always rely on the traditional methods for accessing gauge theories, but use established string theory methods to calculate quantities you might learn about. Abstractly, of course, I have to admit, so far the results we have did not allow us to get any new insights into the M5 brane theory. But what I try to outline is a road towards getting more information about them and learning more about them.